Welcome to the general colloquium of Pniewski and Infeld. It's a great pleasure to chair today's colloquium, and it is even greater pleasure to welcome Professor Rudolf Grimm, who is distinguished scientist from the University of Innsbruck and from the Austrian Academy of Science in Innsbruck. Let me say a few words about Rudy's career, because it's really impressive. He got his PhD in 1989, correct me if I'm wrong, at the Swiss Federal Institute of Technology in Zurich. Then he was visiting researcher and lecturer in Troitsk, Moscow, in the Max Planck Institute for Nuclear Physics in Heidelberg, and at the University of Heidelberg. And from 2000 till now, he is employed as a professor of experimental physics at the University of Innsbruck in Austria. And from 2003, he is also employed by the Austrian Academy of Science. He is a head of the Institute for Quantum Optics and Quantum Information. He is also very active. From 2005 to 2008, he served as a dean of the Faculty for Mathematics, Computer Science, and Physics at the Innsbruck University. At the same time, he also served as a co-editor of the Europe Physics Letters. He is a member, or was a member, of Atomic and Molecular Physics Division at European Physics Society in the years of 2005-2007. In the years 2005-2011, he was a board member of the Austrian Science Fund. He was also a head of the Center for Quantum Physics at the University of Innsbruck, managing director of the already mentioned Institute for Quantum Optics and Quantum Information. And from 2017 till now, he is a head of the Institute of Experimental Physics at the University of Innsbruck. For his achievements in physics, which I will mention at the very end, he got numerous awards and prizes. Already for the PhD thesis, he got a silver medal for outstanding PhD thesis and ETH Zurich. He got Gerhard Hess Award of the German Research Foundation. He was elected corresponding member in 2005, and in 2006 a full member of the Austrian Academy of Sciences. And there are a lot of other prizes and awards. And in 2018, let me mention the last one, at least on my list, which is a Fadejew Medal awarded by the American Physical Society and European Research Committee on Few Body Problems in Physics. Professor Grimm's achievements are truly impressive. He authored almost 180 publications, with the total number of citations reaching 15,000, and his Hirsch index exceeds 50. These are truly impressive bibliographic data, and the most cited paper of Rudy is the review paper on Feshbach resonances in ultra-cold gases, which received more than 1,600 citations till today. But he is very well known for his discoveries. He discovered the Bose-Einstein condensation of molecules, and the publication in Science was cited almost 900 times. He also is an expert in optical dipole trapping for neutral atoms. He discovered an evidence for Yefimov quantum states in ultra-cold gas of cesium atoms, and also this was the first to observe pairing gap superconductivity in a strongly interacting fermion gas. And today, Professor Grimm will tell us about ultra-zimne fermions, the ultra-cold fermions. So, Rudy, the floor belongs to you, and really we hope that it will be a feast after this 6 hours on the faculty board meeting which we spent today.
Yeah, welcome everybody. It's really a great pleasure and honor for me to be here. It's my first actually serious visit to Warsaw. I visited Warsaw 20 years ago, but only changing train at the station, so I don't have too many impressions from that time. What I see is great. And I want to talk now about, I hope I translated this correctly, about the ultra-cold fermions, work that we do in Innsbruck. And you see in the background, you see, maybe can we turn off the light a little bit more? In the background, you see Innsbruck here, surrounded by mountains, and it looked like this about a few weeks ago. It looked like this. And as mentioned already, I'm at the two institutions, the university. Oh yeah, this is getting much better now. Of the University Institute and the Institute by the Academy of Sciences, but these are buildings which are only 150 meters apart, so it's quite easy to be on both institutions. Okay, into Innsbruck you see in the winter. Just to give you some more impressions of Innsbruck, this is a summer picture for the tourists. Here you see our northern mountains, 2 kilometers from here to there, it's 2 kilometers up. And so in the center of Innsbruck, but I mean, you also have a very nice old town. This is from our old town, houses from the 15th century in the old town. And this is the famous Golden Roof, which was just a little bit more than 500 years old and was built by Emperor Maximilian just to show off, to show his wealth to the people. So it's the Golden Roof here. So this is famous. So this is Innsbruck for tourists, and we have many of them. But Innsbruck is also a great place for the scientists, for the physicists, and this is a nice place for the physicists. This is one of our ultra-cold atom laboratories. And just for the non-experts, of course, there are many people here, or most of them, not being in this field. The typical experiment looks like that. So we have a laboratory, and here on this table you have a lot of lasers, laser sources, and there's even a second laser with laser sources, a lot of equipment, electronics, optics equipments, the PhD student working on aligning the laser system. Here you have a control desk, and on this table here is the heart of the experiment. There's a vacuum chamber, an ultra-high vacuum chamber, and there we prepare the ultra-cold gases. And now I want to simplify this picture a little bit. So this is now a sketch of an ultra-cold gas in a harmonic trapping potential. So we can create trapping potentials using magnetic fields, using light, can be very flexible. Here I've drawn a harmonic potential, which we have in most experiments, at least approximately. Or something we can also create boxes, lattices, regular arrangements of atoms, low-dimensional situations. There are many possibilities here for creating these potentials. But let's stay with the three-dimensional harmonic potential during this talk. Then these are atoms here, confined atoms, and they are cooled down to temperatures which are, microkelvin is very hot for us. Usually they are in the nanokelvin region. And this is done by, I don't want to go into details here, by laser cooling and subsequent evaporative cooling. And that's then we reach conditions in the nanokelvin range. Then you see the atoms here, and there we have a choice, a menu of bosonic atoms, total spin, integer numbers, or half integer number, the fermions. They are a little bit less available. And we can also mix them, bring them together, and create ultra-cold mixtures. So having Bose-Fermi, Bose-Bose, Fermi-Fermi mixtures, there's a rich choice of things that we can do. And what makes life then really exciting and interesting is interaction. So these particles interact with each other, and this interaction can be very strong. Okay, that makes life interesting. A few words about the interaction. In the ultra-cold world, at these nanokelvin temperatures, super low collision energies in the pico-electron volt range or something, in most cases, this is completely dominated by S-wave scattering. In most cases, we don't need anything else. We just have to know the S-wave scattering length, A, to characterize the interaction of the system. And now imagine I have a typical interparticle spacing. I have distinguished two regimes. N to the power of minus 1/3 is a typical distance between the atoms in the gas. And now, usually the scattering length is like this, small. Yeah? And the scattering length is small. That means sometimes these atoms or particles collide, and then they move freely. And this is what we call the dilute gas regime. Okay, this is here, weak interactions, and with weak interactions you get elastic collisions. You can understand how the sample thermalizes, and if you then form a Bose-Einstein condensate, okay, you can understand that it's a famous picture of 1995 from the Gila group, and Nobel Prize winning, and you can understand the mean field of the Bose-Einstein condensate based on this interaction here. Okay, that's the weakly interacting regime, I think, which is fully understood and can be very nicely modeled. But how about the situation when we have the typical particle spacing and the scattering length is like this? Yeah? Then this two-body scattering picture breaks down completely. So you can no longer speak of individual just two-body collisions. Everything is kind of a strongly coupled many-body soup. Then it's really many-body physics. Okay, so what happens if I address this regime? I tell you in a few minutes how, with the bosons. What I will see is tremendous losses. So the sample will decay within milliseconds. So what happens? I mean, these ultra-cold atoms, they can form molecules, and the process to do this is a three-body collision. So three particles collide somehow, two form a dimer, the other one stays a free atom, and this takes away the binding energy. Energy and momentum conservation tells you need a three-body collision. And the rate for this is extremely fast. So it's, for most of the experiments, it's bad. You prepare your gas, but it decays within a few milliseconds. Sometimes, I mean, it's not your enemy, it becomes your friend, this process, because in this way, we found in 2004 the 5 first traces of these Yefimov quantum states. So you see if you couple to a Yefimov three-body state, I don't want to go into detail here, but then you couple to this, and this opens up a path of super fast decay. Okay, but this is not today's story. I have another colloquium talk on this, but this is not the story of today. The title says I should talk about ultra-cold fermions. And now back to the fermions. So this is a simplified version of a Fermi sea in a trap. So these are all quantum states, I mean, like a continuum filled with many atoms. You have the Fermi energy, and you have the temperature, which makes the Fermi edge a little bit soft. So this is a degenerate system with a temperature much smaller than the Fermi energy. Okay, and then you ask, okay, nice, the simple system, I fill up all the quantum states up to the Fermi edge, and that's it. Is this interesting? What is interesting? Okay, and I give 3 answers now to the question, why is this interesting? One answer is, if you combine 2 different fermions, fermions have half-integer spin, then you get a boson. So you can compose a boson which is made out of fermions. So that means I can put 2 bosons together, but then the composite particle stays a boson. So fermions are more general, because you can also build bosons from it, and we know it because we can form bosonic molecules from 2 fermions and let them condense, molecular Bose-Einstein condensate. So boson physics is just a special case of fermion physics. Then, fermions are in general the basic constituents of matter. If you look at the electrons, we know they are fermions, but also if you look into hadronic matter, neutrons, protons, and if you look at the quark level, they are all fermions. So if you want to learn something about exotic states of matter, you better work with the fermions. And then there is what we call the universality. It's the beauty of physics. I mean, the universality that kind of certain laws and principles work over many orders of magnitudes of certain quantities, and I want to just summarize it in this table. Here are fermionic systems. On this side is the ultra-cold gas. On the other side is a neutron star. In between, there's a standard metal or maybe a white dwarf. If you compare the numbers in the number density, we typically have 10 to the 18 particles per cubic meter in a very small sample. And the neutron star has 10 to the 44, 26 orders of magnitudes. If you look at the Fermi energy, this is for a neutron star 70 mega electron volt. And for us, it's 300 pico electron volt. But the basic principles are one and the same. It's just a soup of spin up, spin down fermions, and they interact in a quantum mechanical way, which is characterized by the scattering length. Okay, so here are these systems, comparison here, an illustration of a neutron star. I'm not sure whether it really looks like that, a neutron star. But here's the particles in the trap, and there are many analogies on this. For example, superfluidity in the crust of a neutron star, equation of state of a neutron star. Okay, and that's universality. Over a very, very wide range of parameters, the same principle rules. And I can take a system like this to simulate at least some aspects of the neutron star physics. Here is a little bit of history. The first degenerate Fermi gas was produced in 1999 by the group of Deborah Jin, 4 years after the Bose-Einstein condensation. And in the first years, people were thinking, well, fermion physics is boring. You just fill all the levels up to the Fermi edge, and that's it. And the Bose condensates are interesting. But later we learned, I mean, the physics in the fermions is more subtle. I mean, you can pair the fermions, then create bosons, and you have strong interactions. So the physics is extremely interesting. But therefore, I mean, the first degenerate Fermi gas came later, a couple of years later. Then two nice experiments almost at the same time, Randy Hewlett's group at Rice University and the Salomon group at the ENS Paris. And these are textbook experiments. They combine two isotopes of lithium. Lithium-6 is in total a fermion with a total spin, and lithium-7 is a boson. If you combine them in the same trap, they behave very similarly, and you cool them down, and the thermal gas looks like the same. But then you reach quantum degeneracy, and then you see that the Fermi sea, the lithium-6, can no longer shrink. It stays at a certain size. That is what you see. But the Bose condensate gets smaller and smaller, and eventually reaches a Bose condensate. Here's the Fermi sea, the Bose condensate. Very nice. And then, I mean, the field almost exploded. There were some other experiments in Italy, at Duke University, US, at MIT, and we joined the Fermi business as group number 7 with lithium-6, but we joined it immediately with producing a molecular Bose-Einstein condensate because we were lucky with the right conditions. Okay, a little bit of history, and now I don't know, there are many groups all over the world with working on with fermionic quantum gases. Now back to the role of interactions. Remember the bosons, small scattering lengths, large scattering lengths. In the case of large scattering lengths, super fast decay of the gas. If you look at weak interactions, so small scattering lengths, situation is the same. You have elastic collisions, Fermi gases thermalized. Sorry, I have to mention one thing. Of course, fermions can only interact if they have unlike particles. You have distinguishable, and you can do it by either choosing really different particles or by choosing different spin states, different internal states. And then they interact via S-wave. This is what I forgot to say. Only for S-wave scattering for unlike fermions. And then they collide, thermalize, the same as in the boson gas. You can also reach degeneracy in this way. But the real difference now comes when you look at the strongly interacting regime. And there was a remarkable surprise in this field about 15, 16 years ago. And we started to investigate resonant interactions on top of a resonance. I will show later how we do this, with super large scattering lengths. And what turned out, the systems don't decay very fast. They can be super stable. What's the point? What is the difference? I mentioned the decay comes from three-body collision. So you need three particles to come together. And if these are two-component fermions, two spin states, you have necessarily at least two identical particles involved. And this gives rise to a Pauli suppression, which is not enough. So you need some ingredient more. You need a certain kind of special wave function. And then these systems can be very, very stable. That was a big surprise. They can be very stable.
But talking about the repulsive case, yes?
What the?
We are talking about positive scattering length.
I'm talking both about everything close to the resonance. In the positive scattering length side, you can create the molecules on top of the resonance. You have this unitary gas. I will come to this. But the stability argument is true everywhere. But what you need is, in addition, you need a so-called, for the experts, sorry for the non-experts, a broad Feshbach resonance, where the wave function of the colliding particles is halo type. I mean, it's much larger than the kind of classical interaction range. And then you have a Van Conten factor with a deeply bound molecule, which is small. And this is the other ingredient you need. But there you can get collisionally stable molecules, create a molecular condensate, study the crossover to a more BCS-type pairing. The so-called unitary Fermi gas is an exactly resonant system where the scattering length diverges. And superfluidity, that's the topic of interest. So then the field really exploded, and there's a field of strongly interacting Fermi gases with very rich many-body physics. And this has been a major research topic for about 15 years now, maybe 16 years now. With these strongly interacting Fermi gases. Now, what is the next thing I want to tell you? Something which is extremely important. How do you tune the interaction? How do you reach this super strong interaction? And there's a wonderful resonance phenomenon in the ultra-cold world, which we call the Feshbach resonance or Fano-Feshbach resonance. This gives rise to a tuning knob. And this, what we actually change, is a magnetic field, and this controls the scattering. And to make a long story short, the basic principle is you have a sort of molecular potential corresponding to the entrance channel, so the channel where the particles collide. Okay, and this can couple to another channel, which is energetically close, but supports a bound state near the threshold. And then in molecular physics, you have many different coupling mechanisms, weak and strong coupling in different ways. And if this becomes kind of degenerate with the scattering threshold, you get a coupling, and this causes a resonance phenomenon. And the typical shape then looks like this. It's a very typical form of a resonance. Here it goes, the scattering length has a background, goes up, diverges, goes to infinity. From infinity, it goes down back to normal values. Here's a zero crossing, and then again gets to moderate values. That's the typical way. And below that is the molecular state that corresponds to this one. It's not the same color, but it should be blue, this one, yeah. It's a molecular state. We call it the weakly bound molecular state. And close to the resonance point, it couples and gets a parabolic shape. We then call this the universal range. It's particularly important, this range, for the physics. So this is the basic idea of tuning. There's one point I want to make now. This character of the resonances, or maybe the width in magnetic field, can be vastly different. So we know resonances which are milligauss wide, milligauss, and we know resonances which are a few hundred Gauss wide. So many orders of magnitude are different, and this, of course, changes the way you can apply the resonances and also the physics that happen here. And here, the broader resonances are of main interest. Okay, so that's the Feshbach resonance phenomenon. We use it in many experiments, and one example, this is the famous example of the lithium-6 scattering length. Lithium-6 has the lowest two Zeeman sublevels. They show an interaction like this, where you tune the magnetic field, and you get a super broad Feshbach resonance here near 832 Gauss, actually. This is now precisely characterized, extremely broad, and we worked a lot on this characterization of the resonance, which took us years, and also a nice collaboration with theoreticians, whereas Andrea, so he was also involved in the analysis then of the experiments, and we got very accurate knowledge of this resonance. And this is now a tool used in many experiments. I just want to point to some early experiments. Our first experiment was the creation of a molecular Bose-Einstein condensate. If you just cool at the right magnetic field, then the fermionic atoms form molecules. I mean, real molecular physics wouldn't call them molecules. They're extremely weakly bound dimers, and they are composite bosonic particles, and they can condense. And you see it in the change of the shape here and the narrowness of the cloud that comes. And then you can start with this molecular condensate, and you can change the interaction, and you can get across the resonance, and then you can create a more BCS-type system. And that's what we have demonstrated here. You don't see much changes, actually, which tells you that this crossover is something very smooth. So here it's more molecular character, here's more an atomic character, and here's the situation in between the resonant Fermi gas. And here are some more early experiments we performed in Innsbruck. One is about collective modes. One way to study the physics of the quantum gases is you just shake it somehow. You can compress it, then it starts to oscillate. And from precise measurements of these oscillation frequencies, you learn something about the compressibility, equation of state, things like that. And what we saw that at a certain magnetic field, I mean, here we have a low frequency, and there's a sudden jump to a higher frequency. We understand it now as this was hydrodynamic behavior, in most cases superfluid hydrodynamics, and this is collisionless behavior where the particle almost independently oscillate in the trap zone. And here is a measurement of some indications of the pairing gap similar to superconductors with this kind of two-peak structure here. These were early hints on superfluidity in the system, not yet a proof. Proof came later by, two nice experiments, or two breakthrough experiments, one by Debegin's group in 2004 and one by the Ketterle group in 2005. Here they see that there is a condensate of fermionic pairs, which they can convert into molecular condensate. So the proof that there's a condensation effect in these systems, and that is very nice. This is a rotating Fermi gas, and this forms vortices and the vortex lattice in the system. And then it was clear, yes, these systems are superfluid, and learning about superfluidity in these systems is a very exciting topic, and there are still many open questions. Here, something more about superfluidity. You know, in a superfluid, you have a critical velocity. When you move an object at a certain speed, then below a certain speed, nothing happens. There's no friction, and then there's a critical velocity where it heats up. And this was seen at MIT. Here is a rotation experiment, which we performed in Innsbruck. If you rotate the superfluid slowly, that you cannot form vortices, the superfluid part cannot take up angular momentum. Only the classical part can take angular momentum. And we found a way to measure the moment of inertia, which you see here. So there's a suppression of the total moment of inertia due to superfluidity, which you see here. But there's one very important thing missing, one kind of hallmark observation on superfluidity in liquid helium. There's one thing missing. You have an idea what it is? Very important phenomenon that can only happen in a superfluid. Any idea? Has to do with sound propagation? It's the second sound. Okay, the second sound. So, second sound. And that's something we did together with theory group from Trento, published in 2013. I want to just summarize this story on the second sound propagation in a Fermi gas. And so what here, this is a simple sketch of sound propagation in a Fermi gas. Imagine this is kind of a cylinder filled with a superfluid, not at zero temperature, at a finite temperature, but below the critical temperature. And then you exert a certain pressure on it. You hit it on one side a little bit. And what you see, okay, it creates a sound wave. Okay. But then you can do this, what I've seen, is just a density wave, something normal. I can do it with any fluid, just compress it with a pulse, and this pulse density modulation propagates. I can do something else. I can heat it somewhere. I can just apply a short heat pulse. Here in red, heat pulse. And then there's another kind of sound, and you see, maybe you saw in my illustration, this animation, that the sound was slower. And so what you have is, here, it's a heat wave. It's another form of sound. It propagates really like sound. And you have these two sound effects. You have a density wave, which is fast, and you have a heat wave, which is much slower usually. This is called the second sound. And how to understand it? You can understand it in terms of Landau's two-fluid model, so that a finite temperature superfluid is somehow composed of two fluids, the superfluid and the normal part, and the mixing ratio between the fluids is determined by the temperature. Temperature can be something local. If it's locally heated, then the mixing ratio changes. I illustrate it here. Let's say here I have a mixing between a normal and a superfluid. Here's a normal superfluid component. If I compress it, the normal sound wave, then just the N and the S, they are a little bit bigger. There's more normal and there's more superfluid part, but the mixing ratio stays the same. But for the heat pulse, it's hotter, and so superfluid disappears and there's more normal. So there's more normal than superfluid. That's my simple picture for these different ways. So it's local heat means, local, less superfluid and more normal. And this propagates sound like, as Landau showed in his formalism. Now, okay, this is an original article by Landau, and I think the older generation here can read this. So he calculated the two speeds of sound. This first sound, the second sound. Then there are Here's some thermodynamic quantities which we can measure in the gas. I don't want to go into this. But here is the superfluid fraction, the ratio between superfluid and normal. And this is very important, and I want to show you how we can measure it. It's a quantity which is not easily accessible. You cannot simply kind of divide your liquid into here's the super part, here's the normal part. This is not possible because the local mixing ratio is always given by the temperature. But the second sound allows to measure it. And so here is the scheme that we are using. This is an optical trapping beam. This is just an infrared laser beam. Okay. You can use this laser beam to trap the atoms using the optical dipole trap. And this is a cloud of, let's say, 300,000 lithium-6 fermions atoms. And in addition, we have and axially, there's a magnetic confinement which makes this very harmonic. It's a little detail, but it's important for the analysis of the data. There's longitudinal, there's a harmonic trap, and then it's a cylindrical, so the trap cloud looks like a cigar. It's elongated and quite long. What else? Okay, then we have the Feshbach resonance. And the experiments I want to show are done right on the resonance, on the pole of the resonance, 832 Gauss. There's the resonance, and there we excite the system. And then here's the excitation scheme. We have the trapped cloud. The trapped cloud has the superfluid core and the classical outer region. Why is it such? I mean, it's a harmonic trap. And in the outer region of the trap, there's a local Fermi energy which is lower. And so we have the same temperature everywhere, but T over Tf gets higher in the outer regions, and there you lose the superfluidity. So it's kind of a shell structure. Yeah. The inner part superfluid, the outer normal one. And then we take a laser beam. This is an additional laser beam which is repulsive in our case, focused in the cloud. And when we apply these for a short time, it creates a density bump. And this is just a difference in the density in the two clouds, yeah, in the density in the cloud. And this is just a density bump which propagates in both directions. You hit it, and like you do it on a string, there's a perturbation which propagates in both directions. And this moves with a constant speed with time and reaches the normal part, and then somehow, when we don't have any more atoms, it of course ceases to exist. And this is the first sound propagation. This is easy to do. There's an experiment that was done 20 years ago with BEC, maybe 12 years ago with the Fermi gas, and we did it now as a benchmark experiment. Second sound, that's a different excitation scheme. Instead of just abruptly turning the laser on, we modulate the laser. We just have the laser on, and then we shake a slice of the gas. We shake a little bit, and this pumps entropy into the system, heats it up locally. When we do this, we see a density depletion. This is the dark area here, which propagates, but much more slowly. You see, it propagates and then reaches the part where the superfluid ceases to exist. These are the dashed lines, and there it disappears. So this is a local heat pulse which appears as a dip in the signal because there's some thermal expansion in the signal which we use. It's an effect of a few percent in the density. But nevertheless, we can analyze this dark region, and we can plot the pulse position as a function of time for the first sound, and for the other signal, we can we can take the first derivative and calculate the speed. This is for the first signal, and that is for the second signal. Yes, and then we have to interpret what we are doing. And there, I have to show these ones here. This is now the experimental team at that time. Here, the experimentalists here with the PhD student Leonie, the postdoc Meng Kuhn, and then with the Trento group, Sandro Stingari, Lev Pitaevsky, and Jan Huahu. And actually, Lev was originally working with Landau's group in Moscow, and when he was young, and he was at that time already very much involved in understanding superfluidity. And it was very nice to have him on board. And they helped us to understand the situation better. And they've developed a theoretical formalism in the way that you can define local Fermi energy which depends on the axial position. So there's a locally varying Fermi temperature. There's a global temperature which is the same everywhere. And so T over Tf actually is lowest in the center and then increases. So it's like you have all temperature information in one kind of, one set of experiments because you have the inhomogeneity of the trap. And in this way, you can calculate at the end the sound speed over the Fermi velocity as a function of the local T over Tf. That came from the Trento group, and we were then very happy that this was work published in Nature, second sound in the superfluid fraction. And here is the main result. So we observe this one here is the first sound wave, which is almost constant, increases a little bit with the temperature. And these solid lines, these are theory lines. So this is well understood. This served as a benchmark, is well understood. This one here is a signal which gets slower and slower with increasing temperature. And then here's a superfluid phase transition, disappears completely. And that is exactly what Landau here wrote here. Here it's written that this, one of the speeds nearly stays nearly constant, and the other one strongly depends on the temperature, going to 0 at the lambda point. And this is exactly what we see here. It behaves like sound, super second sound in Landau's sense. And then the last step is that we reconstruct the situation for a homogeneous system. T over T critical here, and here is the superfluid fraction plotted, and these are the experimental results. And this is a simple London-type BEC theory, which is obviously wrong. And actually, this green one is what you know from liquid helium, superfluid in a strongly interacting liquid helium. And so the system that we have is very close to resonant behavior to liquid helium. Now you can be inspired by many experiments with liquid helium and do similar things with the Fermi gases. You can do more. In the Fermi gas, you can vary the interaction strength, study the second sound in the BEC-BCS crossover. There are many things that can be done. Actually, we wanted to do this second sound crossover experiment, but then our old apparatus actually had a major vacuum failure and we could not continue. But I know that now other groups are working on this second sound in the crossover. But you may ask the question, okay, liquid helium, many things are known. So is there any new physics now beyond that we can do with the ultra-cold Fermi gases? Okay, and my answer is given here, new physics. And this is a mixture of two different states, two different spin states of a fermionic species like lithium-6. How to address now new physics in these fermionic systems? And one way is to introduce population imbalance. That means to introduce a spin polarization in the Fermi gases. Here you have a majority of the blue ones and only one red one, and here you have the opposite thing. And so here you have a continuous variation. Why is it interesting? It's similar to what happens in superconductors when you apply a magnetic field. You get it shifting you split the Fermi surface, and then there's a question whether the pairing mechanism can overcome these splitting. So that is strongly related to this. And superfluidity and its breakdown with imbalance. And that is a problem that came up a little bit more than 10 years ago, was investigated by several groups, Ketterle group, Hewlett group, Salomon group. And what they observe is in a trap, there are certain regions. In a trap, they observe in the center, there's a superfluid, can be a superfluid paired up fully with same densities. There's a region where you have a majority of one species and the other ones are still there, and then a region where you have only one species. So the trap makes it a bit complicated and leads to the effect that in the center of the trap, there's a balanced population, and the superfluidity in the outer region, there are these different shells. But if you analyze pictures like this, you can get some idea of the phase diagram of this Fermi gas. And here's plotted spin polarization. Here it's balanced. Here it's getting more and more imbalanced. And here's the temperature. And then you learn that, here in the center, there's a superfluid region up to some point. Here it's all the normal region. And there's a so-called unstable region, which you cannot reach in a homogeneous system. What happens then? What happens is a phase separation. A system builds, some part of the system forms a paired superfluid and expels the other one, and they are separated from this. It's a phase separation effect. Okay, and then just remember for later that this is a symmetric phase diagram. If I have just two different spin states, I can call one spin up, one pseudo spin down, but I can also interchange it. So this has to be a symmetric phase diagram. It looks like this, normal, the superfluid center and these unstable regions. But now I can also introduce another way of imbalance. I can use particles of different masses. These are two different spin states of the same species, same mass, but here I use different particles, heavy light here. And that's a new degree of freedom. And so here's a diagram with both new degree of freedom, population imbalance and mass imbalance. Looks a little bit complicated, but there are several regions with very interesting physics. And as a first example, I would like to consider this one, this case, the extreme case where I have one particle, one heavy particle in the Fermi sea of many other particles, one particle. Why is this interesting? Because this leads to what we call quasi-particle physics. So if this particle interacts with the medium, it behaves like a quasi-particle. What does it mean? There's a nice illustration in the textbook by Matuk, 1976, and he explains what a quasi-particle is. And he uses the picture of a horse galloping through a desert. Okay, what happens? The horse galloping through the desert, after a while, will look like this, will be covered by sand completely. Yeah? And then the horse still galloping, it moves with the sand surrounding the horse, but it has a higher mass because it has all this sand cloud around it. It's kind of shielded, you don't see it anymore. Yeah? Also there's always a decay, the sand always is replenished by new pieces of sand. So that's the quasi-particle, shielded, different mass, different energy, and a finite lifetime. These are quasi-particle properties. And we use a similar picture then for our system. Here again, the experimental situation, quite similar to the one before. Here it's a trapped Fermi sea of lithium-6, but here it's a single spin component. So the fermion, this lithium-6 itself, does not interact with itself. Yeah, it's a single identical fermions. And we have the other species, the few potassium-40 particles. It's another fermion, so potassium-40 is also a fermion. And there are a few particles in this cloud. And we do spectroscopy on these particles here. And we have tunable interactions. We know there's a Feshbach resonance, and we have characterized it very accurately, and we can use it for controlled interaction tuning. Now, I have to say a few words about the internal structure. Don't be scared. These are 18 states. I only need 2 states of these ones in the Zeeman diagram. I need the second lowest state and the third lowest state. And I have a kind of a 2-level system. The lower, this state number 2, has a weak background interaction with the lithium-6 atoms. It's just strong enough to make it thermalize. Yeah, and to make it cool down, to thermalize it. But state number 3, this exhibits a Feshbach resonance with the lithium atoms, with the bath. So this can strongly couple to the bath. But this depends on the magnetic field. It happens at a field near 155 Gauss. We have to control it precisely. Now we have the interesting situation of a kind of a 2-level system. One state is weakly or not coupled to the bath, and the other one can be strongly coupled to the bath. And then we have the nice situation that we can address this, the transition, just we drive it by radio frequency methods. Very simple, 37 megahertz you need, and you can apply radio frequency pulses. And the most simple way now to use this is to do kind of spectroscopy, where we start here with a population in the lowest state, which is not interacting or weakly interacting, and we drive this population into the upper state. And then we look at shifts in this spectrum. Okay, and such a spectrum is shown here. We see, here we vary actually the magnetic field. We put it in terms of interaction strength. This is what we would call strongly interacting in the center. And then we see there's, on this side, an upshift of the signal by up to 30–40% of the Fermi energy. And here's a downshift. Here the system is repulsive. Here it's attractive. But then we see that the signal somehow disappears. It fades away. And if you look into this region where it's nearly gone, we see a spectrum which has a narrow peak. So this is the horse. Yeah? And we see a broad background, Fermi energy width. This is the sand. So the horse is still the component of the wave function of the bare particle. And these are all the excitations around us. It's dressed by excitations. From these spectra, we can derive these things. And if you get closer to resonance, the peak completely disappears, and you only see a broad mess of excitations here in a strongly interacting regime. So here are some theory lines that explain that kind of model, what we see. Actually, in the central region, this is what we call the molecule whole continuum. There, molecules can be formed, so a particle from the impurity can grab a particle from the Fermi sea, form a dimer, and this then finally decays. So this can happen in this region between the dashed lines. And the theory here is the green one, the attractive polaron, so the quasi-particle is called the Fermi polaron. And the red one, where we're particularly excited, is the so-called repulsive polaron. And this repulsive polaron, it was very interesting because it was not clear would these quasi-particle live long enough. While the attractive polaron is a stable particle, the repulsive polaron can decay into molecular excitations. And it was not clear what is the time scale. Is the time scale long enough so that it can be important? Or does it disappear and it's completely irrelevant for the experiments? And the conclusion from our experiment is we have a long lifetime. I don't want to go into detail, but we did lifetime measurements on the repulsive polaron, and we show that there's even close to resonance, there's a lifetime which is much longer than the inverse Fermi energy. So this repulsive polaron is really relevant for understanding the behavior of the Fermi gas under these conditions. And this is a measurement of the so-called quasi-particle residue, which is how much the peak is versus the background in simple pictures. But we found a different way to measure it. It also agrees nicely with theory. And very nice for us was to learn just a few years ago, in 2017, 2 years ago, that these repulsive polarons have been found also in a real semiconductor material at the ETH Zurich. There was an experiment showing the existence of repulsive polarons in a thin semiconductor layer. It was very nice that we find new kind of things, phenomena, quasi-particles in our ultra-cold systems, and later in real condensed matter system or semiconductor systems, they find then similar things. So we can stimulate, cross-fertilize to other fields. But here I want to show a few slides on a more advanced way of studying these quasi-particles. And so we can drive a radio frequency pulse on the two-level transition. But now we can drive a pi/2 pulse. So that means you create a coherent superposition of the quasi-particle in its non-interacting, interacting state. So we have a superposition of a non-interacting and an interacting particle. And then, in a paper 2012 by Eugene Demler's group, it was suggested to use this to implement a Ramsey scheme. You create a coherent superposition. You have interaction within the fermionic bath, and then you drive another pi/2 pulse, and then you look at the population. It's a Ramsey interferometry. You can consider it as an atom interferometer in the Fermi sea. And from that, you get better information, unperturbed, because in this time it's completely free of external fields, and it has a lot of advantages as compared to the spectroscopy method I showed before. And from that, we got these results here. I only show this slide on the experimental results. It's the Ramsey contrast, and this shows how much the fraction of the wave function of the bare particle in these polaron. And this is a function of time in units of the Fermi time. This is h bar over the Fermi energy, and it is 4 milliseconds in our case. In the real metal, the Fermi time is 100 attoseconds, very short to measure here. But in our system, this Fermi time is a few microseconds, But that's long enough so that we can carry out experiments on that time scale. And so we can look at this in a kind of time-resolved way. And the main result is what we see is this initial bump here, this transient behavior. That is actually when the dressing cloud is formed. So when the horse is surrounded by the sand. So it's the time scale of, let's say, 10 milliseconds, something like this in our experiment. And that is almost stable and then slowly decays by residual thermal effects. So this is also understood as thermal coherence. We see this for the repulsive polaron. We also see this for the attractive polaron. It's basically the same, only a little bit less pronounced. So that was the first observation of quasi-particle formation in real time. And these are some theory lines. So we stimulated several theory groups to model these things. And these are their results by two different models. I don't have time really to get into detail. They are completely complementary. And now there's a very nice understanding of these, what is going on there. Just want to show the team, the experimental team at that time, and a group of PhD students, postdoc, and the senior professor, Jorgen, and all our theory collaborators. This was very important to work together. And in our field, it's really very nice. I mean, we have many opportunities to work together with theoreticians and to cross-fertilize, and we show new exciting experimental situations, many things we don't understand, we got then explained, but also theory gives us new ideas to develop things further, and I hope we can also establish such a collaboration here with Warsaw and some new systems that we have in the lab. And so here's one goal of these experiments. It's about the so-called Anderson's orthogonality catastrophe. So that's the old idea by Anderson, who published many, many, many exciting papers. And the point is the following. He showed you have a Fermi-sea, a degenerate Fermi-sea, a large fermionic system degenerate. And then if you bring a single impurity into this Fermi-sea, which interacts with the Fermi-sea, then you think it's a very small perturbation. A small particle in this huge fermi doesn't do much. But he showed that the whole many-body wave function is orthogonal to the original one. And it's a massive change to go from the simple Fermi-sea to the Fermi-sea with the impurity. And many processes are blocked in that way. And one way to look at this is using this time domain spectroscopy. And Demler group predicted that in these time spectra, there are three different regimes. An initial quantum dynamics where the dressing cloud is formed, that's shown here. And these are just different schemes of many pulses, and the simple Ramsey scheme is this one. Here's a thermal decoherence regime, which we have seen. And then there should be a regime in between, so it's plotted as in a double log scale, which gives straight lines with some wiggles. And that's a power law decay. And the prediction is that the manifestation of the orthogonality catastrophe, that you would see a power law decay behavior. And maybe we have a chance in the experiment to see this, but turns out we need really low temperatures, a % of the Fermi temperature. That's a bit hard. We reached 5% of the Fermi temperature, but here you have to go below 1%. And so we have to work hard on cooling to further pursue this idea. Okay, so I come back to this slide and my last story on interaction in the Fermi-sea. We have investigated the polaron problem here. But now it's very natural. You extend it and you go a little bit more into this direction. And here you have a few particles, and that's a picture of interacting quasi-particles. It's a very important question in Landau's Fermi liquid theory, not only the existence of single quasi-particles, but how would they interact, the quasi-particles. There's not much known. There are a couple of theory papers, almost no experiment on this. And that's what we are working now on, increasing the polaron concentration and measuring what is going on. I don't have results on this, okay, but we are working on that. And I think we have good ideas how to address it. It's not very easy. But then you ask, how about further? Can we increase the population and then enter into superfluid regimes? Now I have to tell you some secrets. This was done done before with the lithium-potassium system, with the Feshbach resonance. And so experiments here require long lifetimes, but the problem is these Feshbach resonance we use in lithium-6, potassium-40 has the problem that the stability is not very good. The Pauli suppression effect is there, but it's weak. Factor 3 or 4 we have observed. And this is not enough. The resonance is good for doing the polaron physics. This needs only short time scale, but longer time scale to study superfluidity. Unfortunately, it's not a good resonance for this. Then you say, okay, if you cannot use this resonance, use another resonance in the system. But the system does not offer any other good resonances in the ground state. It decays, everything decays. Nature is not so kind to us in this system regarding the Feshbach resonance. It's a wonderful resonance for the quasi-particle physics. We use it further, but not for the superfluidity. So what can you do? The way out is you have to think about other systems. And now I come to the last part, short part of my talk. I want to introduce a mixture of dysprosium 161 atoms, these are fermions, and potassium 40. So 4-to-1 mass ratio. And the goal is to create, which we have not yet reached, I mean, it's a high, very ambitious goal to create novel superfluids and to start emerging many-body phenomena related to that. Okay, I want to show, dysprosium potassium. You may ask, why do they pick dysprosium potassium? I have to give some answer. And the answer is here in this kind of table. These are all the 8 fermionic atom species which have been brought to degeneracy. Okay, and the number just shows the mass ratio. And then I come up with a catalog of criteria. I cannot go through all the criteria. One is the mass ratio. You want to have a considerable mass ratio, but not too big, because then again the system can become unstable because of Yefimov states and things related to this. So the good mass ratio is between 3 and 10. And finally, there are some other criteria on interactions, possibility to find Feshbach resonance, and this leaves 3 systems. And one is this lithium-chromium system, and that is some work experimentally pursued in Florence. And here, theoretically, it's considered here lithium-chromium mixtures. That's a very important and very interesting candidate. And there are 2 other ones, and these are combinations of potassium 40 with either dysprosium or erbium. And we selected dysprosium because lasers are a little bit easier and things like that. So that's our choice. And now I want to show just a few slides to give you an impression where we are and to tell you that it's a very promising candidate. Okay, here is again a simple phase diagram for the balanced Fermi gases. This is the motivation. What is interesting? Okay, and you have seen this before, more colorful. There's a superfluid region, 0 polarization, and you have population of FR means forbidden region. This is the phase separation region. This is normal. This is a tricritical point in the phase diagram. And if you can now compare it to a phase diagram, this is on resonance, unitarity, exactly on resonance, divergence scattering length. Now I will look into a phase diagram, which is a mass imbalance system, different masses. And then it becomes asymmetric, and it looks like this. And the right-hand side looks similar to this one, is relatively boring. But on the left-hand side, interesting things happen. There's a so-called Lifshitz point where the Cooper pairs become unstable towards some kind of finite momentum pairing. And there are also symmetry breaking states like the buzzword in our field is now the FFLO, full de Ferrel-Lagrange-Chinikov state. This is a super fluid state where the pairs have finite momentum and the modulated ordering parameter. And all these things should happen on this side when you have a majority of heavy atoms. And then you look at the temperature predictions, and temperature calculations show you this should happen in an experimentally accessible range. If under exotic conditions you find something also in the mass balance case, but under conditions like per mil of the Fermi temperature, something which we never realize experimentally, but here it appears in a realistic experimental range. And so this is the regime we want to look at. And so theories, there are some theories on the market. I mean, it's a very difficult thing, but they basically agree, not really in quantitative detail, but in the general structure that here are the interesting things. Here's something from a Chinese theoretician from Hangzhou. And here is the site with interesting phases, majority of heavy particles. Basic message is the same as before. Interesting things happen here. And this here now is for us our holy grail, the holy grail we want to find and then explore further. This is our kind of main driving force with these new experiments. And now how the new experiment, of course, you need a motivated team of people, and these are the Innsbruck team now working on the dysprosium-potassium experiment. We started to set it up 5 years ago from scratch, but now we are getting first results. And the first thing what you have to do is you have to build a vacuum machine. Or you can also say the first thing you have to set up your lasers, but you have to construct a vacuum machine anyhow, and I have a picture of the vacuum apparatus, and you have to do laser cooling there and prepare the sample. Then the next important step is doing evaporative cooling, and we found a way, I don't want to go into details, to produce a double degenerate system of deeply degenerate dysprosium atoms and degenerate potassium atoms. And then comes the third step. Mission is not yet accomplished, but it's on a good way. It's the identification of to understand the Feshbach resonance spectrum. And the key question now is, are there broad resonances? And I want to show promising preliminary results. I skip these details. This is about our deeply degenerate Fermi gas. You can just believe me, we have a deeply degenerate mixture of both species. And now comes the key question. Do we have this knob, the control knob? Can we change the scattering length? Is it stable enough? Do we get a suppression of loss? If the answer is no, we have to think about something else we do with this system. I mean, there are many possibilities, many isotopes. There's a backup strategy. But if the answer is yes, then we really could open this new field of exotic superfluids in fermionic systems. Okay. This is the first Feshbach resonance spectrum in a narrow magnetic field range. This is just less than 1 Gauss. The whole scale is 1 Gauss. And then you see narrow features, losses, where both dysprosium, blue, and potassium are lost. Narrow interspecies resonances. We see them. It's easy to find them, but they are useless because of the large losses. They are also too narrow for controlled interaction tuning. And that was a starting point for months of searching, resonances in the whole spectrum, scanning magnetic fields over a very large range. And then we found something like this. So I have to explain this picture. This is not a loss spectrum. Before it was particle number after a certain hold time in the trap. This is temperature. Okay, and we create a system with a fast evaporation ramp, which is not in thermal equilibrium exactly. So the dysprosium is colder, about 300 nanokelvin initially, a little bit more, 350 maybe, than the potassium, which has close to 700 nanokelvin or even 800 nanokelvin. Then we put it into our trap and let them interact for a short moment, only 20 milliseconds. And then we see there are regions where nothing changes here in the temperature imbalance, and there are certain regions here where there is some fast thermalization going on. And this is an indication of fast elastic collisions. So we know the cross-section there gets up, and that means the scattering length gets up, and these are clear signatures of resonances. And we have carried out many more experiments on different features, resonances, zero crossings, and so on, and the current knowledge of this looks like this. So this is what we believe the scattering length is in that region, and we can also give numbers for the poles of the resonances and the zero crossings, the background scatterings for the experts here. And we can also for the experts, calculate some kind of pole strength, how strong the resonance really is. This is the relevant quantity. And this is about 800 times Bohr radius times Gauss, which is already quite nice. And this is something which makes us very optimistic. In particular, we don't see on this resonance significantly enhanced losses. That's the main point. So if we go on resonance, there's not much loss. The system is stable for a second or so. And then the last thing I want to show, we zoom in this narrow region. And we see this we look at potassium here. Dysprosium shows similar behavior. We see there's some loss feature, and there's some heat feature at the same time. This is number, and this is measure of temperature, loss and heating. But this is not where we expect the pole of the resonance. And something like this is known in the field, and this is a fingerprint of molecule formation by three-body recombination, populating this weakly bound molecular state. Similar things have been observed in lithium-6. And that makes it also very, very optimistic. On the pole, very little losses, a feature which shows molecule formation. And now we have to understand these in more detail. That's the present status, but I think it's very promising for the future experiments. We are quite excited, but we have to understand many more things in detail. Okay, and now it's time, I think, to conclude. And I want to do it using this simple picture. So what is it? It's kind of illustration on the phase diagram of the fermionic mixtures. And so this is phase diagram of fermionic mixtures. On this axis, I have interaction strength, something I can vary with the Feshbach resonance. Here I have the population imbalance of the two different species. And here I have the mass imbalance degree of freedom. Then I have a fourth dimension, which I cannot draw. This is the temperature. Okay. Now the first experiment, the second sound experiment. This was right in the center of the cube. Balanced mixture, fully resonant, and no mass imbalance. And we varied, so the temperature somehow, and studied the sound as a function of temperature. That's the second sound. Okay. Then there are many experiments. I have not shown really examples. I've shown 2 pictures or so on BC-BCS crossover physics. So you vary the interaction strengths and see how the properties of the system change, like chemical potential and compressibility and all these things. This is quite well explored. Then there's the field of imbalanced Fermi gases, the polarized systems, where you have, as an extreme case, single particle in the mass of the other ones, so the polarons, repulsive and attractive. This is all with mass balance system. And our work now, our work is somewhere here. So we introduce the mass imbalance, where we also have studied, I've shown you an example, this repulsive polaron, also the attractive one on this side. But the really exciting things now, there are many open questions with the polarons, or what happens if I put a light particle in the mass of the heavy one, and all these things. There's interesting physics. But I think the real challenge here is to get here, to have some population imbalance of more heavy particles. And there are all these exotic superfluid regimes. So there are the novel superfluids, and there's our holy grail, which I hope that we will be able to access maybe in a few years from now in the experiments. Okay, so that was my quick summary. And I can now come with one slide of general conclusion. So ultra-cold fermions, I hope I could convince you they are really a very rich playground for interesting many-body physics, strongly interacting systems. There are many challenges ahead of us for both experiment and theory. With this statement, I want to close and thank you for your attention.
Thank you very much, Rudy. Professor Rzążewski.
In this most recent work with dysprosium and other atoms, dysprosium has a relatively strong dipole-dipole interaction. Mm-hmm. Does it play any role from the point of view of your experiments?
Yes, it plays a role. It plays a relatively simple role in the fact that we do the evaporative cooling. So what I said in the beginning was too general. It was not correct that you have to work with 2 different spin states, something like. In the case of strongly dipolar particles, and that's a dysprosium atom has the largest magnetic moment you can get for an atom. It has 10 times the Bohr magnitude. That means in collisions between particles, you have it's squared. It's 100 times stronger than you have it for typical alkali atoms. And then actually, so you can get even at low collision energy, because of the long-range nature of the interaction, you can have elastic scattering with a cross-section, universal cross-section, which is like rubidium atoms in a condensate. And we use this for the evaporatively cooling. So we cool dysprosium, a single species component, and we cool the potassium sympathetically. That's for the cooling. And then for the physics, of course, it's responsible for many Feshbach resonances somehow. It can complicate the situation. We don't know, what actually causes the resonances, what kind of coupling we use. But you see in the dysprosium spectrum alone, you see a zoo of resonances. You find, per Gauss, you find 10 resonances or more, narrow resonance. Yes. And people studied chaos, a chaotic spectrum. But it seems that if we go to higher field, then they all overlap and it's just a fluctuating background. It's not that bad. That's about the Feshbach resonance, about then the physics. Then if you look for the fermionic, for the pairing physics, we know that in the dipolar system, the Fermi surface is a little bit deformed. So it could be that we have, for the potassium, a spherical Fermi surface, and for the dysprosium, somewhat elliptical Fermi surface. And so there will be matching depending on the direction. And that could be some pair formation, but in a not isotropic way. So that would be, the effect is not very strong. I mean, the deformation of the Fermi surface is just a few %, but nevertheless, perhaps it would change the physics.
I have also a question about this imbalance system. When you have this mass imbalance, I can imagine the box potential. Then mass imbalance means that there are different excitation energies, but for both species. Yeah. But I can also imagine the harmonic potential, and if you can master and experiment such situations that you have the same excitation frequencies for both species, then mass imbalance will result in different special extension of these two functions.
It's an excellent question. That was exactly a point, but I took out these slides of my talk, yeah, because I thought it'd be too special. Sorry, but try to explain it. It's actually we can realize a situation, even in this harmonic trap, so that particles have the same density distribution. We call it magic trapping conditions, and the key is the polarizability of the trap, so the depth of the trapping potential. And there is a simple condition, so mass times E Fermi, the Fermi energy, should be constant for both species. And you get the same in the zero temperature regime, you get the same density distribution of both particles. You need conditions, let's say, here we have a mass factor of 4, where the polarizability for the heavy one is just a factor of 4 smaller than the one for the light one. And then you can get these matching conditions everywhere in the trap. You can modify the conditions if you want to say, I want to have a population which you have 2 to 1, and then I have a formula how to calculate the polarizabilities. And then you look, what is the polarizability in this system? And you find that there is a factor, not 4, but 3.2 between the polarizabilities. So in this infrared trapping light we are using, the 1064 nanometer, we are close to these transitions, to these magic conditions where you can get a kind of situation, matching conditions over the whole trapping potential. And if you choose the right wavelengths, we think there's a magic wavelengths around 970 nanometer, where you can get these exactly to this condition. So I think that's, so in this way we can overcome the problem of the harmonic trap. Otherwise it gets very complicated.
Other questions or comments?
I have 2 questions. One is that, as I understood, we can either have there was studied a mass imbalance or polarization imbalance, right? But in principle, if we have roughly, like in this last regime, when we have roughly the same amount of heavy and light atoms, and can we then introduce also a spin polarization imbalance inside each species?
No, but so spin imbalance is the same as population. I mean, in this, I mean, usually in the mass balance system, they use different spin states. So therefore, population imbalance is the same as spin imbalance. So one should use the term population imbalance. This is more
okay.
general.
So
that's, but you can get, maybe that's your next question already. But also, if you have a population balance, if you have the same, you can get a kind of pairing of the particles and get into superfluid behavior, but that's more conventional superfluidity, a little bit more like BCS pairing. There's not this symmetry breaking, these other pairing. It can become superfluid, but in a more conventional way, on resonance. But if you have both mass and population imbalance, then you enter these exotic regimes.
Oh, okay. So now I understand, yes. The second question was just, I was curious, when you showed these plots where there are different number of atoms with, like, when you measure free body losses.
Yeah.
What, like, how do you what is the way to measure this, like experimentally, the
simple
number
loss
of
spectrum
atoms?
with the narrow loss features, this one, yeah? Oh.
Yes, there was this plot with changing magnetic field and number of
Yes,
atoms
yeah,
in
okay,
each
okay.
in
Yeah.
each species. So how is the number of atoms measured? That's just
Okay, general detection. So the number of atoms is always done by absorption imaging. So we just take a kind of camera image of the atom cloud, but in a way there's a laser beam weak laser beam on resonance propagating then on the object, and then it's collected by the camera. It's kind of a shadow imaging, we call it. And from that you can get very nice, you know the absorption cross-section, and you can get nice calibrated number of atom images. Just absorption image. You can also collect them again in the sum of traps and monitor fluorescence. But the calibrated one is the absorption imaging. It's a standard technique. I should have explained it, but it's so standard. Yeah, it's absorption imaging.
Other questions? Janusz?
I do appreciate the beautiful experiments you were talking about, but I would like also to hear your opinion. I mean, by studying these rather artificial systems, what have you learned about the more abundant systems you mentioned in one of your tables? Like, you know, what did it produce for us as an insight into studying, I don't know, nuclear physics, physics of neutron stars, or... Yeah.
So you can...
Could you please give your view on this?
I think the question is, it's very general. It's a question about our whole field. So why do we build these kind of cold atom systems as simulators for other systems? You can interpret this as a little bit fashionable, this word, a quantum simulator. You can study certain types of interactions, models on the lattice, and here in the systems, and you can learn then certain aspects. I mean, the systems are very clean and very well defined, which you don't have in, let's say, condensed matter materials, which are not so well defined, and you can test different models. And I think you can, basic theoretical models, which are, I mean, non-trivial different many-body models, you can test very accurately. You can provide experimental benchmarks and see how correct are these models, or they capture the reality. And one question, for example, that connects somehow to the neutron star, it was a big question in the field if you have two kinds of fermions, two spin states, and they have a very large scattering length. And this is actually the case in the neutron star. In the crust of the neutron star, you have exactly this situation. So they're close to, together, but the scattering length is much larger than the interparticle spacing. It's a resonant gas, and then you wonder what is the chemical potential of this situation. Simple situation, I mean, you are on resonance, you have a degenerate system, what is your chemical potential? And it turns out that it can only be a rescaled version of the Fermi energy. And this number, I mean, it's a famous Birch problem, this number was unknown. And now this has been accurately tested. I think it's 0.375 or something like this. And there's a very nice example how even more refined theoretical calculations and new experiments so came to some conclusion on this number, which is central of the many-body physics. So I think it really helps to improve also theoretical models to describe certain things. In optical lattices, for example, Fermi-Hubbard models, which are very difficult to calculate on a computer, and these things. I think that's the interesting point. There where theory becomes difficult, complicated, computational, very heavy, then we can have these quantum simulation systems and test things very accurately. And there comes the progress.
Other questions, comments? If not, let us thank Rudy again.
Thank you.
And the colloquium is concluded. Thank you very much.